Okay, so we're going to talk about chapter 12 today, PLC subroutine functions. With a little luck, when we get done, should be able to describe the function of a subroutine, create a ladder diagram that incorporate one or more, create ladder diagrams for the subroutine, use input devices to call a subroutine, use compare instructions in the main PLC ladder to call subroutine, and explain the difference between interrupt and regular routine or subroutine. Subroutine concept. Additional ladder logic files are called subroutines. Specific subroutine is executed in PLC program scan, depends on the state of an input device or result of a compare instruction. Main ladder diagram or main file is program file number 2. Always creates file number 2 automatically. You can't delete it. Okay. If you wish, in order to break your logic up into smaller chunks, logical chunks that make more sense, like a manual routine, a fault routine, an automatic routine, that kind of thing. Those are pretty typical. Some people put the real world outputs in their own output file, and then in the logic you set internal bits, B3 bits, and then those bits are what actually turn on and off the physical I/O in the subroutine file. So you can write programs that consist of several modules or subroutines and not one lengthy single module program. I say it makes sense for you to break it up into smaller logical chunks. Programs that are written with subroutines can be tested individually to ensure accuracy, and they can be called from the main program. Actually, there's 2 ways to do it. I've seen it both ways. Your main program, ladder file 2, has the global stuff that you need that's common to all of them, and then the jump to subroutine instructions. The other way to do it is for each subroutine in your main ladder file, you have jump to the first one. At the end of that one, you jump to the next one. At the end of that one, you jump to the next one, and so on. The only problem with that is when you get finished jumping into all your subroutines, it has to remember which way it went in so it can find its way back. Okay? So, well, we'll get into that further in here. Subroutine 1 and 2 are called from the main program in that example there. You're probably not going to have that much logic between your subroutine calls. The program counter holds the address of the next instruction is going to be executed. After executing the instructions in subroutine, the return instruction, the very last line in the subroutine program, causes the program counter to return to the main program. So if you jump out of the main program into subroutine on rung 3, goes to subroutine, processes it. When it hits the return instruction, it comes back. It's going to pick up where it left off at rung 4 and continue on. Does that make sense? Okay. processor continues executing the instructions in the main program after it returns from the subroutine. The stack is just a space in memory where prior to jumping into the subroutine, the processor creates a stack which holds the contents of the program counter, flag register, and general purpose registers. So it basically takes the status of all of the current memory, pushes it into another section of memory to hold it while it processes the subroutine. And when it comes back, first thing it does is grabs the information that it pushed on the stack back off and back into memory so that it can continue where it left off. Call instruction causes the processor create a stack and then executes the instruction or the subroutine. Return instruction pulls the contents of the memory back off the stack, places the contents back in the process registers, and program execution resumes from there. The instruction that you use to get into a subroutine is JSR or jump to subroutine. Okay. The JSR instruction can be conditional or unconditional, either one, depending upon how you want to use it. So top one there is conditional. It only jumps if this evaluates as true. Okay. Unconditional is when you jump in the subroutine for every time. Okay. So that's what the difference is between conditional and unconditional. The latter example with conditional logic. You have to create the routine, the subroutine file before you can use it in JSR too, by the way. So in order to create one, you open up your controller organizer, program files, right click on program files, select new, and then you can tell it which program number you want, what the name of it is, and a short description of what it's doing. Okay. The names where you put auto, manual, fault, output, whatever it is. And then the descriptor, you got several more characters that you can use. This is default routine or blah, blah, blah. Okay. This allow online edits checkbox is checked by default unless you have some reason that you don't want people to be able to edit the subroutine. We'll leave it checked. If you uncheck that box and you need to go back and fix the routine because you made a boo-boo, it won't let you do it. You have to go back into the source code, recheck the box, re-download, and all that stuff. Just nickels worth free advice, as they say. Return from subroutine. The subroutine file itself must have an SPR instruction at the beginning of the program to indicate that this is a subroutine file. Not done. If it is not letter file 2, it's a subroutine. Period. The return instruction at the end is required, cause it to return back. No, it's not. Every file that you create, the very last run in that file, has that instruction. You cannot delete that run. Won't let you. When it sees end, it treats it exactly like it does a return. Okay. Good programming practice says use SPR and RET in every subroutine file, which you don't strictly have to have one. Okay. One of the cool things about the return instruction, though, it does not have to live at the end of your program. So if you have you need to adjust the pressure inside a vessel of some sort, and you're doing it by modulating valves or controlling fan speed or whatever. When you need to make an adjustment, you turn off your conditional logic in front of the return, so that everything after it also processes. Or when you're not wanting to make those adjustments, you turn the conditional logic off, evaluate as false. When turn it on, so that it evaluates as true, and then when it hits that line, it'll return and won't process anything below it. Does that make sense? I feel like I'm kind of not explaining that correctly. Okay. If the return is in the middle, and there's more logic below it, if this evaluates as true, then you will return and none of this logic down here gets processed. Okay. If it evaluates as false, then it just keeps going until it gets to, you can have more than one return in your program too. Or until it hits the end instructions file. Okay. Does that help? Applications of subroutines. Most industrial applications, lengthy programs are required. Large diagrams are usually divided into several subroutines. Each one of those subroutines is written and tested, and the shorter main programs used to call subroutines for different conditions. And if you don't have any faults in your system, nothing is off kilter, then you don't have to call the fault subroutine that processes the actual faults. If you are in automatic mode, you don't have to call the manual subroutine. In manual mode, you don't have to call the automatic subroutine, that kind of stuff, okay? That is an example program. That would be ladder file 2 there. So as you're getting inputs on input 0, increment your counter, and then when the accumulated value of the counter is equal to 10, it's going to jump into subroutine 3. If it is less than 10, it's going to jump into subroutine 4, and if it's greater than 10, it's going to jump into subroutine 5. And then if you had input 1, resets the counter. Okay. Been doing this a really long time. I've never seen anybody use counters as their conditional logic for subroutines. Not once. So in the subroutine, there it shows the SBR subroutine instruction, and then there's that B30 is just that dummy bit, because SBR is an input instruction. You must have an output on every rung. So it's not doing anything but saying, hey, there's an output here. So it will unconditionally turn on the green pilot, motor 1, and return back to the main. Okay. So it doesn't specify which subroutine it is, does it? So what does it say that our counter is equal to 10? So it's going to hit the jump to subroutine, come in here, turn on the green light, turn on motor 1, return, come back, and it'll pick back up right here on rung 2. If it's equal to 10, then it's not less than 10, so that evaluates as false, moves on to the next one. Equal to 10 is not greater than, so it just moves on to the next one. Okay. And then second subroutine turns on yellow pilot motor 2, third is red pilot light motor 3. Interrupt. Interrupt is it's an unconditional, no matter what you're doing, go process that subroutine. Which, if you have a separate fault routine, depending on what the fault is, you may need to, whatever it is, you're going to stop, go process the fault routine. You know, maybe you have a tank full of acid that's getting ready to run over and your high limit hits. You know, I don't care what else you're doing, stop and go turn on the alarm bells and the whistles and the flashlights and, you know, all kinds of other things. Two main types of interrupts: selectable time and I/O. The I/O would be your high limit. STI, selectable timed interrupt. If you have a mission critical sensor that you need to read that updates faster than your program scan is. If you need to read that every 10 milliseconds and your program scan is, 30, every 10 milliseconds it stops what it's doing, goes and processes that routine, comes back, picks up where it left off. 10 milliseconds later, it stops whatever it's doing, process, come back. Okay. The um, interrupt time, it has been a really, really long time since I've used STI on 500. The minimum is 1 millisecond and max is a couple of seconds. I can't remember. That's the other thing too. You can, if you only need to sample it every once in a while, you can do an STI that says only jump that subroutine once every 10 minutes or, whatever it is. Okay. STI is used to interrupt scan a program at a specific time. Intervals specified by placing the time interval value in status file register S. Or you guys ever looked at the S2 status file? Well, we're almost done with the slideshow here. I'll show you after we get done. IO interrupt. Cannot use a standard discrete IO module to accomplish an IO interrupt. Has to be a special one. So not just any Logix Pro we're not doing, so we don't worry about that. Okay, so let me get my RS Logix pulled up here real quick. Okay, so under your data files, you have O0 output, I1 input, S2 status, that's the controller status. Okay, whenever you open it up, it defaults to a structured radix. You can change that to binary so it looks more like the others. It makes it a lot harder to read. So, processor mode. Word 1 bit 0 through word 1 bit 4 will tell you what mode it's in. Last time this program was saved, the controller was in remote run mode. On power up, go to run mode behavior. You can set your program so that when the controller first powers up, you can prevent it from jumping straight into run mode, which is what it would normally do. I can't think of any good use case scenarios for that. If you program your system correctly, you don't need that kind of feature. The first pass, which is word 1 bit 15, that is the very first scan as soon as the controller powers up or switches from program to run. Well, any mode, from any mode to run. For one scan, that bit is high. And then turns back off and never comes on again. Until you switch out of run and back into run, whether it be cycle power or however you do it. That is really, really useful if you have OTL instructions in your program, because a latch bit will survive a power cycle. Okay, so just turning it off and turning it back on does not clear latch bits if you use an OTL instruction anyway. So, good way to do it is some more here. Good way to do it is to set all your latch bits in a single, well, the same word, couple of words, whatever it ends up being. I put a descriptor on the word level in the bit file. And then I use that in my program somewhere. It's going to ask me for a descriptor for bit 0. It's just going to inherit the label that I gave B through 4, the word level descriptor, unless I change it to whatever, something else. Then that overrides. Okay. But yeah, I've got a whole bunch of these in there, and they are connected to OTL instructions. When I first power up, I can either say manually unlatch, 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 or the best way to do it, that's why you put them all in the same word. I can never remember where this instruction I'm looking for is, but that first scan bit. Okay, let's do this. Do a clear instruction. Set to the word level. So now, on first scan, it'll write all zeros into every one of those bits. So, on first scan, it writes a 0 to all of them. So it basically goes, resets them all at once. Okay. Free running clock, you can use individual bits out of the free running clock. If you need light to flash, half second on, half second off, or whatever, you can use a free running clock and use the individual bits out of it. That's 4. Okay, that's your time base. So since this is running in binary, it's on, off, on, right? XIC, when it's on, it's going to evaluate as true. When it's off, it's going to evaluate as false. And it's regular intervals. Okay. Junk about the processor nobody really cares about. Scan times. Overflow trap, which is right there. You do a boo-boo in your math and you try to divide by a 0, or put a number in a register that doesn't fit 16 bits, you can go up to 65, 535. Anything more than that, it doesn't fit because there's only 16 bits. You'll get a math overflow. If you don't do this overflow trap unlatch, the very last thing in your program, and something like that happens, it'll fault your controller. If you put that in there, it won't. And then, of course, there's bunch of other stuff in here. Errors, if you have an error, the error bit set. And then there's a description, tells you what it is, forces, and all kinds of stuff. So it's a neat file to poke around in. Okay, so any questions before we try the lab?